Hello everyone. Today's topic of discussion is operation of indicating instrument. Indicating instruments are the analog type instruments where we have seen there is a pointer scale arrangement. The pointer moves over the scale and it shows the value of the unknown quantity. Now, how the indicating instruments operates means what is the working and what is the different driving force or what are the different torque which are required to operate the instrument. To operate the indicating instruments, three types of force or torque are required. What are the different torque? Deflecting torque, controlling torque, and damping torque. So to properly operate the analog type indicating instrument, combination of these three types of torques are required. And to generate the torque, there are some driving force, there are some system inside the instrument. Deflecting torque is required to move the rotating part or moving part of the instrument. There are several effects which are used to generate the force or deflecting torque, which are the different effect. There may be some magnetic effect, heating effect, chemical effect, or electrostatic effect, or electromagnetic induction effect, which actually produce the deflecting torque. And this deflecting torque actually the driving force to move or rotate the moving part or the pointer over the scale. The method which is used to produce the torque depends upon the type of instrument. Means for PM's time instrument, permanent magnet is used. For moving iron type instrument, electromagnet is used. So depending on the type of instrument, the torque is generated. Different torque is generated in different way. Controlling torque is required to make a finite position of the pointer. Depending on the deflecting torque, the pointer moves over the scale and it goes to a final position. Without the controlling torque, what will happen? It may goes to the maximum limit or maximum range of the display. And when the instrument is not in operation, the pointer must come to rest or pointer must come to the zero position. So without this controlling torque, what will happen? The pointer may goes to the maximum position when the instrument is in operation, and when the instrument is not in operation, the pointer may go beyond the zero position. So that's why controlling torque is required. To provide the controlling torque, there is a control system. Two types of control systems are there. One is the spring control, another one is the gravity control system. So for spring control, there are some hair springs which are attached to the moving system. See in the figure, two hair spring or control springs are there. Two springs are attached with the moving part. This is the spindle and pointer is attached with the spindle. Two control springs are fixed or attached to the spindle. Whenever the pointer rotates or the spindle rotates, the spring actually compressed. So a force is exerted in opposite direction by these two control spring, and the controlling torque will act in opposite direction to the movement of the pointer. The controlling torque is proportional to the angle of deflection of the moving system. How much angle is deflected, the pointer is deflected, controlling torque is proportional to the deflection angle. In case of controlling torque Tc is proportional to the angle of deflection theta. We can write Tc equal to Ks into theta, where Ks is the spring constant. Deflecting torque Td is proportional to the current flowing through the instrument I, or Td equal to Ks into I. At equilibrium, we can write controlling torque equal to deflecting torque Td. So from this relation or from this equation, we can write theta equal to I, or theta proportional to I. That is, angle of deflection is proportional to the current which is flowing through the instrument. For gravity control, there are two weights which are attached to the moving system. One thing you must note, for gravity control, the instruments must be placed vertically. It is not working properly if it is placed horizontally. Two weights are attached to the pointer. When pointer rotates or deflects, the position of the weights are also changed. The weights are known as, one weight is known as the control weight and second weight is known as the balance weight. So when the pointer deflects, when pointer changes its position, the control weight also changes its position. Due to the gravity, the control weight will generate the controlling torque. Damping torque, after going to the final position, the pointer oscillates over the final position because of the inertia of the moving part. Due to the inertia of the moving part, we will see some oscillation over the final position of the pointer. So to reduce the oscillation over the final position, we require some damping torque or damping force. Damping torque is provided. There are different ways to generate the damping torque. Three types of damping systems are there. One is air friction damping, fluid friction damping, eddy current damping. Fourth one is the electromagnetic damping. The damping torque is proportional to the speed of rotation of the moving system. Mathematically, it can be expressed as Tv equal to Kv d theta dt, where d theta dt is the rate of change of the angle, deflection angle with respect to time, and Kv is the damping torque constant. Three types of damped systems are there. One is under damped, over damped, or it may be critically damped. And what is the under damped system? The response is little bit more oscillatory. Over damped system, for the over damped condition, the response is sluggish and it rises very slowly. Critically damped condition, when the response settles quickly without any oscillation, the system is said to be critically damped. That's all for today's lecture. In the next lecture, I will discuss about the PMMC type instrument, permanent magnet moving coil type instrument. Thank you.